All right, it's time to ponder a little bit more complex application of the motion equations, still dealing with instantaneous values. So our situation is we have a car that's traveling 50 miles an hour along Wooster Pike for 3 miles. Reaching Terrace Park, it slows to 40 miles per hour as it travels 28 meters. We want to calculate the total time that the car is driving. Well, if we kind of sketch out what we have our car, and it travels 3 miles at 50 miles per hour. But this 50 miles an hour, that's constant. It doesn't slow down. It's just traveling at 50 miles per hour. Now, when it reaches Terrace Park, then it slows down. So it continues to travel forward an additional 28 meters, and it slows down to 40 miles per hour. So that means in this interval, v changes, but in our first interval, before we got to Terrace Park, the velocity was constant. Well, when your velocity is constant, then you don't have initial and final values, and the motion equations aren't very useful to use. Instead, your average equations apply. So then we can use v equals delta x over delta t. Over here where the velocity changes, then we do have an acceleration. We have initial velocity of 50 miles per hour, final velocity of 40 miles per hour, and then our 28 meters, that would be how far we traveled. That would be a delta x. So then we will need a motion equation over here to be able to calculate what our time is. So given those values, we can use the motion equation. Delta x is 1/2 times vf plus vi times delta t. Now, before we can plug anything in, we're going to need to do some conversions. Our 50 miles an hour and 40 miles an hour are going to need to convert over. Remember 1609 meters in a mile. So 1 mile, 1609 meters. 1 hour, 3600 seconds. So that means our 50 miles an hour is going to convert over to 22.3 meters per second. Since I didn't leave myself enough room over there, I'm going to write it over here. And then when we do the same conversion on the 40 miles per hour, that's going to convert to 17.9 meters per second. We also need to convert the 3 miles over. That's our initial delta x in the first interval. And so multiplying that by 1609, that delta x becomes 4827 meters. So then keeping our two separate intervals, first interval we want to solve down for time. So then this is going to be 22.3 meters per second is equal to 4827 meters divided by delta t. Multiply the delta t over. That'll be 22.3 delta t is equal to 4827, and then divide both sides by 22.3. That's going to give us a time interval for our first part of the motion of 216.46 seconds. On our second part, where we are changing the motion, now plugging in our values, our delta x over here is 28 meters equals 1/2. Final velocity was 40 miles an hour, which is 17.9 meters per second. Initial velocity was 50 miles an hour, which is 22.3 meters per second. And then time is what we want to solve down for. So then mathematically, we're going to add the 17.9 and the 22.3 to get a number. We're going to take half of that number, and then we're going to divide that over to the other side. So then when we do that algebra, we solve down, and we get 1.39 seconds. Now, what we want to find is the total time. To be able to get the total time, that's going to be the time it took during the constant motion and the time that it took during the changing motion. So then we're going to add these two time intervals together to get the whole thing. So delta t total, when we add those together, 217.85 seconds. So sometimes you will run into situations where you have two different distinct segments of the motion. In this case, constant, and then an acceleration. And you have to segment and keep the information given about each section separate and decide what equations to use. Ponder physics.